Hello and welcome back to another QUT game design and implementation video. Today we will cover a topic that lends itself more towards the artificial intelligence side of things, but is still useful for the average game designer to know about. When designing an AI agent, it is useful to have an understanding of some of the things that are possible straight out of the box in Unity, but also what needs more consideration and scripting effort. This video will therefore cover three major topics. Firstly, we will discuss Unity's new default navigation system and how we can easily employ it for use in games, particularly for things like NPC actions such as patrolling. Secondly, we will explore how to implement a simple line-of-sight detection system that is both efficient and effective. Thirdly and lastly, we will extend this system to handle the detection of the closest target within view when multiple targets are within range and line of sight. This degree of targeting priority is important, as sometimes it's not just the closest target you want to deal with. We will discuss this more later on. Unlike its predecessors, Unity 5 has a handy new navigation system which uses a combination of generated 2D geometry, which are baked from the environment's traversable geometry, and some straightforward pathfinding algorithms used to find the shortest path through it. The geometry is what is called a nav mesh, with polygons containing traversal information along their vectors for use by nav mesh agents. Potential agents will use a pathfinding algorithm to move through this territory, which is most likely a form of the popular A-star search algorithm, but set up for navigation purposes. Without going into too much detail, the algorithm employs a depth-first search in a tree-like fashion, evaluating navigation nodes using a permissible heuristic and placing them into open and closed sets based on said evaluation. The technique results in a shortest path possible return and is used to guide the vast majority of NPCs to their destinations in the games that you play today. So before we get started, I will just mention that a completed version of this entire project is actually available for download via link in the description. This video has some rather lengthy scripting sections, and typing it up all by hand today would be rather laborious. The following scene contains an NPC, a ground environment, a few walls, and 4 patrol points. This NPC already has a script set up to patrol between these points, but is just missing a technique of navigating around the walls in the environment. We will add this in the form of Unity's nav mesh navigation system. So to do that, we will first access the navigation panel just by going to Window, Navigation. And that should open some kind of panel in your UI that has these settings here. What we first want to do is actually, just to demonstrate this process, is we'll just bake the ground. So having the ground object selected in your hierarchy, just press bake. And you should get this blue mesh with a couple of polygons associated with it, containing a bit of the information that I discussed previously. What we want to do, first of all, is actually make it so that these walls cut sections in this nav mesh, dividing the nav mesh up slightly more so that there's a little bit more detail and a little bit more information that can be accessed. So just selecting the 3 walls in the scene, I will go to Object, and first of all show you the technique of making these navigation static but not walkable. So if we go back to bake now, and I just hit that, you'll notice that segments of the nav mesh have been carved out. Now this is great if we know where we want to place our objects in the scene, but if we're still moving things around, or if we have elements of our game world that are maybe moving around, even if they're, say, other enemy NPCs, one other technique of doing this is actually adding a nav mesh obstacle component. So if you go to Component, Navigation, Nav Mesh Obstacle, we can actually add a Nav Mesh Obstacle to these 3 walls, And if I hit carve here, what you'll notice is that when I bake it again and move these things around, you'll see that they'll deform the nav mesh slightly as well. I'll just untick the navigation static component because it seems to be playing up a little bit. And I'll bake that again. But yes, if you do want to move your walls around the scene, or move any kind of object around the scene in a little bit of an easier fashion that's not going to set to be static baking of the nav mesh at this point, just give them a nav mesh component and make sure their carve setting is set to on. Now also in this scene is a NPC. This NPC already has a script set up to navigate between the 4 patrol points that are set on the scene, which are just these black spheres located under patrol points here. So in order for us to do this, we could write a bit of code that will just move us slowly between the points, but we want to actually use this nav mesh system that we have attached to the ground. So to do that, what we actually need to do to this NPC is attach an additional component called a nav mesh agent. Now this will give it some properties to do with steering and movement, movement speed as well, which you are free to adjust. But now we can actually go into that script and add an additional library, which will be using Unity Engine.ai, as well as setting up a link to that component that we just added. So we want to make a link to a nav mesh agent, and we'll just call it something simple like agent. And within start, we will make agent equal a get component call, which will be to said nav mesh agent. Cool, so this NPC already has that script set up to navigate to those patrol points. This is being done in a cyclic fashion, in the sense that it's just a simple conditional that's checking for the distance between the current patrol point using a patrol point index. And if it's near the current patrol point, it increments the patrol point index to go to the next one. If, however, the patrol point index becomes greater than or equal to the length of the array, it gets set back to 0. So it goes in a circle, essentially. What this is missing right now, however, is a command communicating this agent to use the nav mesh system that we have applied to it. So the final line that we're going to add here is just a simple call to our agent component to set a destination, being the patrol points in question, specifically the patrol index, or the patrol point that we're currently referring to. That patrol point's transform dot position. Oops. And that should be it. If you go back into Unity now, we should get this NPC moving around in the manner that we anticipate, using, in particular, the nav mesh at its disposal. So what you'll see here is that this NPC should be moving around the environment, but taking great care to avoid these walls that we have baked into our scene. Setting up line of sight detection is a problem a lot of students end up having with their games, and is usually not one that is addressed in an elegant or efficient manner. Typically, students end up attaching something like a massive collider to their NPCs, which is both expensive and problematic as it requires using events to collect information. The solution I will provide here is much more effective, as it simply relies on a bit of vector math to calculate if a target is within a field of view. The technique I have employed in the following solution is known as the barycentric point-in-triangle technique. It relies on using some basic trigonometry and vector math to determine if a point is within a triangle on a two-dimensional plane. It is very efficient and can be extended relatively easily to systems that require more complex field of view resolutions. As you can probably articulate, it is an excellent method to use for simple field of view detection systems in games, and is what we will use today. To accommodate this, I have implemented the generic barycentric vector math already, which you can find online easily enough, and I'll put a link for that in the description. We will use this as a true or false return function, passing the information regarding an enemy target and our viewing frustum over. As such, we will need to set up these variables in script and call them in a manner that is logical. To accommodate for line of sight checking, I'm encapsulating the method call in a conditional that raycast checks if the enemy is not occluded by geometry in the scene first. So back in Unity, I have set up an enemy with a script that changes its color simply if it is targeted by the NPC, but it won't work at this point until we set up our NPC's viewing frustum. And to do that, we can make use of just simply using a couple of game objects that you can put in the scene to the left and slightly to the right of our NPC, giving that field of view triangular effect. So to hook these up correctly, I have made a couple of empty game object components in our script, and I've just dragged them in there like so. The enemy I've also directly referenced in the NPC script by simply dragging and dropping it into an enemy component. This is something that's temporary and probably something I will change for the next stage of this project. So to view all of this in effect, I'll just press play. What you should see is that the enemy is obviously visible to our NPC straight off the bat. It's within its field of view and there is nothing in the way regarding line of sight. However, if I do just pause this game and say put everything in front of this wall, if I run the game now, you'll see that while the enemy is within the line of sight, is within the NPC's viewing frustum, it is actually not within line of sight because obviously the wall is obstructing it. If I just move this enemy forward slightly, you'll see it change red. It's within line of sight, behaving as you would typically expect. So the next and final part of this video is demonstrating just how we can extend this paradigm into a more complex line of sight detection system, that being targeting, say, a specific enemy within our field of view. Typically you will find that this is just the closest enemy target, say for instance when you move a group of NPCs in a particular direction in the games that you play. That is what I've implemented today, but you should know that you could extend this system further to do something more intelligent, such as targeting the enemy that has the lowest health. Because we are storing our enemies in a list, we do have the capacity to filter through them or even sort them based on some arbitrary property that these enemies have. So for this process to work, I will first of all need to store said multiple enemies in some kind of container. In this case, an array. I will collect these enemies in updates, like so, using the tag system that we've probably discussed in previous videos at this point. An additional container will be used to keep track of the enemies that are within our current field of view, that being a list. Now, within our closest enemy detect function, I go through each of the enemies in the enemy array, adding or removing them from our field of view detection list based on their positioning, and then check to find which of those enemies within that list is the closest one within line of sight. Notice the familiar raycast checking system here, but also its placement within a series of conditionals that determine if it is the closest visible enemy. Eventually we will find the closest enemy, but also we allow for a degree of error checking, setting our closest enemy to be null if there is nothing within our field of view or nothing within line of sight. So do take some time to look through this part of the scripting component in the project demonstration linked in the description. This is something that you'll probably need to walk through to get your head around to any great degree. So to see how all of this works together, let's just jump back into Unity. And again, I've set up the scene so that it accommodates this functionality straight off the bat. If we just press play now, you'll see that the closest enemy that is within line of sight will be detected and set to be the closest enemy target. What we can do to demonstrate if our code is working correctly or not is, first of all, we can just move this wall away slightly and you'll see that this becomes the closest enemy target instead of that one. However, if we were to move this enemy instead into our field of view, you'll see that this one becomes the closest enemy target instead. Again, if we were to just drop this wall straight in front of everything, you'll see stuff being occluded and accounted for correctly, which is exactly what we want our system to do. So, to end off with this video, I have set up the scene to have a degree of automation for your convenience. We have created an NPC that will randomly patrol an environment using Unity's default navigation system, but it will also encounter and target the closest enemy within its field of view and line of sight. What your NPC chooses to do from this point is up to you, but also what its targeting priority could be is also something that you should consider adjusting in the system. Again, proximity does not necessarily need to be the logic that drives an NPC's targeting, and the basis of more intelligent agents revolves around implementing systems that take other gameplay elements into consideration as well.